relaxation time of a high molecular weight polymer. The viscosity and relaxation modulus of the polymer is given. The stress relaxation behavior of high molecular weight polymer can be represented by the Maxwell relaxation model, which can be represented by this equation. Now, we can convert the viscosity and modulus values in similar units, which is Pascal second and Pascal, by dividing poise and dynes per centimeter square by 10. Now putting them into the equation, and on simplification, we find that the relaxation time is 55.5 hours. Next question is, what will be the true stress when a sample is elongated by 50%? Sample dimension and force is given. As we know, true stress is force divided by actual or final cross-sectional area. We can determine the cross-sectional area of the sample after deformation and then divide the force by the final area to calculate true stress. So, after deformation, the new length will be 45 mm, and since volume remains unchanged, the initial volume will be equal to new cross-sectional area multiplied by new length, which is 45 mm. On simplification, we find that the new cross-sectional area is 10.67 mm square. Now, dividing the applied force, which is 165 Newton, by new area, we can find the true stress. And in order to get stress value in Pascal, we need to convert area from millimeter square to meter square. After calculation, the final answer is 15.5 megapascal. In question 15, we need to find the damping peak at 10 to the power 4 Hz frequency. The Tg of the polymer and damping peak at 1 Hz is given. To solve this numerical, we need to use Wlf equation. As I have previously mentioned, Wlf equation is one of the most famous and useful equation in polymer science. It helps to determine the change in glass transition temperature, modulus, and viscosity of the polymer with increasing temperature and frequency. So, we can write Wlf equation in the frequency form like this. To find the damping temperature at 10 to the power 4 Hz frequency, we have to first calculate the frequency at actual glass transition temperature, which is 100 degrees C. By putting the values of given Tg, frequency, and C1 and C2, which has universal values of 17.44 and 51.6 respectively near Tg, we find that the glass transition temperature was measured at 0.001475 Hz frequency. Now, we can use the same Wlf equation and use the Tg value and two known frequencies to calculate the glass transition temperature or damping temperature at 10 to the power 4 Hz. And the value is 133.2 degrees Celsius. The correct answer is B. In this question, we need to find the number average molecular weight of the polymer at 99% conversion. The monomers, adipic acid and ethylene glycols are in equimolar ratio. Number average molecular weight of the polymer can be represented by this simple equation. To calculate this, we have to find degree of polymerization and molecular weight of the repeat unit. To find the degree of polymerization, we can use this simple equation, which is for two monomer system. For equimolar system, R is equal to 1 and the equation reduces to very simple form. As percentage conversion is given, we can put that value in the equation to calculate degree of polymerization. To calculate molecular weight of the repeat unit, we can simply add the atomic weight of all the atoms and then divide it by 2. The molecular weight of the repeat unit is 86. As we know degree of polymerization and molecular weight of the repeat unit, we can calculate the number average molecular weight of the polymer by simply multiplying the two. And the answer is 8600 grams per mole. Next question is, there is glass fiber resin composite with 30 volume% fiber. The elastic modulus of resin and fiber is given. Now the question is, what will be the percentage strain when 100 megapascal stress is applied parallel to fiber direction? To solve this question, we have to determine the stress on the fiber, and then by dividing stress by modulus of the fiber, we can determine the strain value. So let's imagine on application of 100 megapascal stress, composite deformed by a very small amount dl. Considering no slippage condition, the strain for both fiber and resin will be same. So the strain for fiber and resin can be written as the stress divided by respective modulus. Equating strain on fiber and resin, and on simplification, we find simple relationship between forces on fiber and resin. Now, the total force is the sum of force taken up by fiber and resin. Therefore, we can replace force taken by resin by total force minus force taken by fiber. As modulus of both fiber and resin is given, we can put those values in the equation and solve them to get the fraction of force taken by fiber. As total force is stress multiplied by total area, we get force on fiber in the form of total surface area. Now, stress on fiber is force on fiber by fiber area, which is also in the form of total surface area. So on simplification, we find stress in the form of Pascal. Now the fiber strain will be just dividing stress by fiber modulus, and the value is 0.4%. This is relatively simple question. Here we need to find the weight of fiber that need to be mixed with 1 kg of phenyl ester to prepare composite with density of 1600 kg per meter cube. Density of fiber, resin and composite is given. So let's imagine x kg of fiber need to be mixed with 1 kg of ester to have a composite with the density of 1600 kg per meter cube. So the volume of fiber and ester in the composite will be mass divided by respective densities. So the density of composite will be 1 plus x divided by calculated volume. This density will be equal to 1600. On simplification, we find that x is equal to 2.54. So 2.54 kg of fiber need to be mixed with 1 kg of resin to have composite with 1600 kg per meter cube density. In question 21, we need to calculate viscosity average molecular weight of the polymer. The viscosity average molecular weight of the polymer can be represented by this simple equation. As constants K and A is given, also values of intrinsic viscosity is given. So we can simply put these values in the equation and calculate the molecular weight. After simplification, we find that viscosity average molecular weight of the polymer is 16.3 kg per mole.